All right, everybody, good afternoon. Welcome to fall semester of 2025. I am pleased to be picking up the student seminar Wednesday at 2:30. Today's speaker is none other than Sofia Avila Nevarez. So Sofia comes to us from Virginia, where she did an Associate of Science from Northern Virginia Community College in 2019. After that, she got a Bachelor's in Science from Virginia Tech in December of 2022. After that, she came to AOS in fall of 2023, working in my research group. We were brainstorming ideas of what to do for her master's thesis, and then I happened to have a conversation with Larissa, who's sitting right here in the front, who suggested that we looked at the processes leading to moist tropical heat waves, and then the rest is a history that will be presented in the seminar that is happening right now. So welcome all, and Sofia, without any further ado, go ahead.
Okay. Thank you, Angel. Can everybody hear me? Well, good. Thank you. So yeah, thank you for the introduction, and I'll be presenting, as Angel said, the moist thermodynamic processes leading to the onset of moist tropical heat waves. So before we begin, I just want to give a quick outline of how this talk will be outlined. So the first thing I want to do is introduce heat waves and try to compare and contrast the differences between dry and moist heat waves. And then I'll introduce a couple of important concepts in tropical meteorology pertaining to the leading order balances in the tropics. And then I'll introduce some recent advances that have been happening in the tropical moist heat wave research. And from then, I'll introduce our research goal. And then we'll go through the data and methods and show our results and how we're interpreting those results. And then finally, I'll summarize everything and try to suggest some directions for future work from there. Okay, so what are heat waves? Heat waves are long periods of unusually warm, high surface temperatures, and they can be very dangerous. So on average, there have been around 400,000 deaths per year between the years 2000 to 2019. So they're clearly interesting or important to be studying. And these heat waves can usually be categorized as either being dry or moist heat. So what are the differences between moist and dry heat waves? This figure is from Ha et al. 2022. They were investigating heat waves over Southeast Asia. So on this left panel here, they were categorizing the dry heat waves. On the x-axis, we can see the temperature. The y-axis, we can see the relative humidity. And they also calculated a heat stress index. And they categorized this heat stress as either being safe in the greens or dangerous towards the reds for human health. And we can see here in the dry heat wave case that when we have the low relative humidity, but we increase the temperature, the heat stress doesn't really get to that danger zone. That standpoint, are there any differences, physical differences between the two? So this figure is from Kong and Huber from 2023, where they try to find whether dry and heat waves days overlap with each other. So to find their dry heat waves, they use regular air temperature, and for their moist heat waves, they use the wet bulb temperature. And they wanted to see if these days overlap with each other. So on this color bar here, the blues are suggesting there's no overlap between the two, whereas the reds, they do overlap with each other. And we can quickly see that in the tropics and the subtropical region, these two types of heat waves do not overlap with each other. So this kind of motivates us to think that there could be a different physical mechanism that can lead to moist heat waves. So I just mentioned that they use the wet bulb temperature. But what is the wet bulb temperature? I want to define it because we're going to be using it a lot. So the wet bulb temperature is the lowest temperature that air can have when you cool it through evaporation. But what does that mean? That sentence makes no sense to me at all. So I think a better way to understand it is how we interact with the wet bulb temperature. So imagine that you're outside and it's hot and sunny, right? So you start to sweat in order to cool down. The air is dry, so you can cool off by evaporating that sweat. So that means that there's a low wet bulb temperature. So you can stay cool and happy. However, if now you add moisture into the air, now it's hot and humid. If you try to sweat and evaporate that sweat, the air cannot accept your moisture anymore. So you get hot, and you get sad, and you can die, actually. So be careful about this. So the web bulb temperature is actually a pretty attractive measure to use in the tropics. But in order to understand why, we have to understand a couple of concepts first. The first being the weak temperature gradient approximation, or WTG. And this just basically states that in the tropics, we have weak mid-tropospheric horizontal temperature gradients. And we can kind of see this in this animation here. This is showing a 500 hectopascal temperature, and these are the monthly means using AR5 data. So you can see as the months go by, in the higher latitudes, the temperature gradients tend to change a lot, right, because of the seasons. However, throughout the entire year, between around 20 south, 20 north, the temperature stays relatively the same in the mid-troposphere. So this suggests that there's a nearly uniform temperature distribution. And the way this works is through tropical convection. So suppose you have a cloud that acts as a heat source, right? So now you have a temperature anomaly from that heat source. The tropical convection also triggers some gravity waves that help distribute this temperature anomaly. So this is happening continuously in the tropics. There's also a secondary circulation that helps cool the cloud adiabatically. So in total, you have this balance between diabatic heating and adiabatic cooling. And this is the basis of WTG balance. And a lot of the tropical motions are actually in WTG balance. There are a few exceptions, such as mature tropical cyclones, and at a more planetary scale, ENSO signature is also not in WTG balance. Another important concept in tropical meteorology is this known as quasi-equilibrium. And this basically states that in the tropics, there's a large-scale forcing that pushes the atmosphere towards this point of instability. However, this instability is quickly consumed by convection. So you end up with a tropical atmosphere that is approximately moist adiabatic and neutrally buoyant. And it should be important to note that this instability is actually undilute. And this is the same as, if you're familiar with this, CAPE. So any changes in CAPE under quasi-equilibrium would be approximately 0. So hence, this buoyancy would be approximately 0 under quasi-equilibrium. Something that branches off of this is called entraining quasi-equilibrium. This is the same thing as before, except now you're adding the effects of dry air entrainment. And if you take a look at this plot here, just focusing on the bottom x-axis is the buoyancy with that dilution incorporated into it, and on the y-axis is the precipitation. And if you just focus on the red dots here, you can see as you start to increase the buoyancy and approach 0, the precipitation starts to quick up very rapidly. So you can interpret this as the instability being used up by that convection. This leads us to conclude that the entraining plume buoyancy is also approximately 0. But it should be important to note that the undilute component of this can also be non-zero. And this buoyancy relationship works very well with precipitation. So under WTG and quasi-equilibrium, you can make some pretty interesting assumptions. So this is a schematic from Byrne and O'Gorman 2013. On the x-axis, we have potential temperature. On the y-axis, we have the height. The dashed lines show the lapse rate over land, and then the solid lines are the lapse rates over ocean. So under WTG, we can assume that the temperatures are equal if you go high up enough in the atmosphere. And under quasi-equilibrium, above both of their LCLs, we can assume that the lapse rates are equal and approximately moist adiabatic. So from this, we can draw the conclusion that over land and over ocean, the equivalent potential temperature of both are approximately equal. However, in the tropics, we like to use the moist static energy. So the moist static energy is just the sum of the dry static energy and the latent heat. The dry static energy is just the sum of sensible heat and the potential energy. And the moist static energy and the equivalent potential temperature are actually pretty similar to each other. So if we look at this example sounding here from Chavez and Peters, 2023, not 2013. On this left panel here, on the bottom is the potential temperature. On the y-axis is the height. And if you just focus on the solid line, which is the equivalent potential temperature, you can see that on the right panel, which is the static energy, the moist static energy and the equivalent potential temperature are actually evolving or like change very similarly to each other with height. So this just reassures us that these two variables are analogous to each other. So now going back to the wet bulb temperature. The wet bulb temperature, the lowest temperature air can have when you cool it by evaporation. So this is both an isobaric process and an adiabatic process. So this means that its enthalpy is conserved. From this, we can use it to estimate the moist enthalpy. And the moist enthalpy and the moist static energy are pretty similar to each other if you assume hydrostatic balance. So basically what this means is that the wet bulb temperature and the moist static energy should have a really strong relationship with each other because they're physically equivalent. And we do see this. So this is a figure from Zhang et al. 2021. On the x-axis, you have the subcloud moist static energy, and on the y-axis is the surface wet bulb temperature. And the dashed line is the theoretical relationship between the moist static energy and the wet bulb temperature. And you can see by the shading here that a lot of the points here do kind of match up with this theoretical relationship. So we can be reassured that the wet bulb temperature and the moist static energy are physically equivalent. So this leads us to conclude, based on the same study here, that the maximum wet bulb temperature is kind of set or constrained by the weak temperature gradient and quasi-equilibrium, such that any changes in the maximum wet bulb temperature over land are approximately equivalent to any changes in the wet bulb maximum over the ocean. So just to reiterate, WTG states that there's nearly uniform mid-tropospheric temperatures in the tropics, and quasi-equilibrium states that there's near-surface instability that is quickly used up by convection. The atmosphere is approximately neutrally buoyant. And the surface wet bulb temperature and the moist static energy is constrained by these two theories. However, if you try to apply the weak temperature gradient and quasi-equilibrium to understand heat waves, it doesn't really work, because in order to have a heat wave, by definition, you need high near-surface moist static energy or wet bulb temperature. You need high near-surface instability, right? That will not trigger convection. But as we saw under quasi-equilibrium, that instability is quickly used up by convection. So we're going to have to think a little bit more about this. So recently, it's only been proposed that tropical heat waves be thought of under this WTG quasi-equilibrium framework, but they don't incorporate entrainment. A lot of the research focusing on entraining quasi-equilibrium only focuses on its relationship with precipitation, but not heat waves. Until recently, like about a year ago, this paper by Duan et al. In 2024 kind of hypothesized that dry air entrainment is what helps intensify these moist heat waves. So this is just a diagram that I summarized their main conclusions from. So let's just assume that you have a boundary layer that becomes unstable. So its buoyancy is going to increase and it's going to want to rise. The air is going to want to rise. However, if you introduce dry air entrainment, in this case, at around 850 hectopascals in the low level of the atmosphere, this entrainment is going to reduce the rising air buoyancy so that convection is suppressed. You have that high near surface instability building up, and a heat wave will occur. So this leads us to our research goal. What are the processes that lead to this that can then result in the heat wave? So the data I'll be using is ERA 5 data from the years 1980 to 2018. I'll be using daily mean values for all the variables on a 1 degree by 1 degree spatial resolution. And I'll be using pressure levels from 1,000 hectopascals to 10 hectopascals. And these are all the variables. All the variables that you're going to see after this is from this data set. The methods are mostly going to be lag composites, and I'll be explaining that in more depth as we go on. But the first thing I want to do is find where this moist heat is occurring the most, right? So what we did here in this figure is we found the top 5% of the wet bulb temperature, which is around 25 degrees Celsius. And we wanted to find where this threshold is being exceeded most often. So as you go to the reds, that's where this is being exceeded most often. And we are only going to focus on 4 regions for this presentation. So we're going to be focusing on the Yucatan Peninsula, highlighted in the black box. We're going to be focusing on a region near India, a region over East Asia, and a region over Northern Australia. So the way we calculate these heat waves is, suppose I want to take the heat waves of this region, right? What I'm going to do is simply just area average the wet bulb temperature so that you get a time series or a time record. And then I'm going to find where that top 5% threshold is exceeded for at least 3 consecutive days. And then we also decided to perform some spectral analysis on the wet bulb temperature. And to do this, I first removed the monthly mean from each grid cell, and then I removed the monthly mean from each grid cell. And then I area average these anomalies in each of the 4 regions. And the way the power spectra is computed is by taking the time record that you have, splitting it into equal length segments, taking the fast Fourier transform of each of those segments, and then finally just averaging them all together to give you a power spectrum. And the way the figures are set up is kind of like this. So on the x-axis, you will have the frequency. So low frequency, longer periods, high frequency, shorter days. And on the y-axis is the power, or the strength of the signal. And wherever you see the highest power, if that power is significant, then we want to retain those signals, or those frequencies. So here are the plots for each of the regions: Australia, India, East Asia, and the Yucatan Peninsula. The dashed gray line is the 99th significance level. And I'll just summarize here that in all of the regions, the highest power is less than 40 days, and the lowest power that is still significant is 5 days or above. So following this, we're going to be applying a 5 to 40 day bandpass filter on all of the variables used after this. So next is the lag composites. So the way we compute this is by removing the monthly mean, and applying that 5 to 40 day bandpass filter. And then we area average these anomalies over each region. And we find when the wet bulb temperature is exceeded first, and that would be our lag day 0. And then we create the lag 7 days before this day 0 and 7 days after day 0. So in total, we have 15 days to analyze. We're also going to be calculating the lower free troposphere buoyancy, or the LFT buoyancy. And this is following Ahmed and Neeling 2018 and Adames et al. 2021, where they find that the buoyancy averaged over this region, 850 to 600 hectopascals, can generally capture the effects of entrainment. And this is usually expressed as the total buoyancy is equal to some undiluted component of the buoyancy minus some dilution. And I'm going to be showing you the whole equation that we used. So this first term here is the buoyancy at the LFT. This next term here is just constants capturing the effects of gravity and temperature. This next term here is the undiluted component of the buoyancy. So this is the moist static energy near the surface minus the saturated moist static energy in the LFT. I'll also be referring to this as the boundary layer instability. And this last term here is the diluted component of the buoyancy. So this is the specific humidity at the LFT minus the saturated specific humidity at the LFT. I'll also be referring to this as the subsaturation. Okay, so first I'll be showing the composites for temperature, the wet bulb temperature, and the buoyancy. So I'll take a sip of water first, because Okay, so this is the lag composites over India. On the x-axis, we have the range of lags, the days. On the left y-axis is the temperature. On the right y-axis is the buoyancy anomaly range. So the red line is the 2-meter temperature. The blue line is the 2-meter web bulb temperature, and the black line is the buoyancy. So first, let's just focus on how the temperature is evolving. So we can see that prior to the onset of the heat wave, the temperature anomalies are slightly negative. However, as you approach day 0 and a little bit after that, they become positive, which is reassuring because this is a heat wave. The buoyancy, however, is increasing prior to the heat wave, but decreases at the onset of the heat wave, and it even becomes negative. So we have increasing buoyancy prior and decreasing buoyancy afterwards. Over East Asia is very similar. The temperatures are slightly negative prior to the heat wave and become positive on the onset. The buoyancy is slightly positive prior to the heat wave, but it decreases as well and becomes negative at the onset of the heat wave. The Yucatan Peninsula is very similar as well. So we can see here that the temperatures are non-zero, but close to 0 prior to the heat wave. They become positive at the onset, and the buoyancy increases prior and decreases and becomes negative at the onset of the heat wave. Over Australia, the temperatures are slightly negative prior to the heat wave and positive at the onset of the heat wave. The buoyancy here prior to the heat wave is also positive, but it remains positive throughout the duration. However, I will note that there is a local minimum. There is some slight decrease in the buoyancy. However, it doesn't become negative like the other regions. So the web bulb temperature and the temperature increase while the buoyancy decreases. So what we're going to do next is break down the buoyancy into its undilute and dilute components to see which one of those terms is contributing to the evolution of the buoyancy. So here is the same format as before. The mint green line is the subsaturation, the orange line is the boundary layer instability, and the black line is the buoyancy. You can see right away that the boundary layer instability does not change at all throughout the duration of the heat wave. The buoyancy is mostly being explained or followed by the subsaturation, as you can see by the green and the black lines here. Over East Asia is a very similar story. The boundary layer instability doesn't really seem to change at all. And it's the subsaturated term that's evolving the same way as the buoyancy. Over the Yucatan Peninsula, same story here. The boundary layer instability is not really evolving throughout this range of lags. It's the subsaturation term that's kind of closely following the evolution of the buoyancy. Over Australia, we do see some more contribution from the boundary layer instability, especially at the onset and onwards. However, I will note that the pattern of the subsaturation very closely follows the total evolution of the buoyancy. So we can say that this is largely at least explaining most of the buoyancy in this region. So the subsaturation is largely responsible for the decreases in the buoyancy. And we kind of expected this from the previous study that looked at entrainment and the moist heat waves. But to get a clearer picture of what's going on, we might want to take a look at the entire column. So what we're going to do next is we're going to look at cross-sections of a specific humidity and temperature. So to do this, we're going to do it in a lag pressure composite form. So first, we area average the anomalies for each region and for each pressure level between 1,000 hectopascals and 300 hectopascals. And then we create the lags and composite all of the 4 regions into just one giant lag pressure composite. So first, I'll be showing the specific humidity and omega, or upward and downward motion cross-sections. So here on the x-axis is the days, and on the y-axis is the pressure levels. The shading corresponds to specific humidity anomalies. So positive anomalies would be more indicative of a moist and the negative anomalies will be indicative of dry anomalies. The contours are contours of omega, so the dashed lines are negative omega, so that means upward motion, and the solid lines are positive omega anomalies, so that means that's indicative of downward motion. So what I first want to focus on is the days prior to the heat wave, right? So here we can notice that there are some moist anomalies, but they're not just happening like near the surface or in the lower free troposphere. They're happening throughout the entire column. And then in this region as well, we do see some negative omega anomalies. So this indicates that the column is moist, but there's also upward motion. Now, a little bit prior and on the onset of the heat wave, we see this dry anomaly starting to form, specifically between 600 to 400 hectopascals. And this is the region where we start to see as well some downward motion evolving, yeah. And we'll also note here that near the surface, there is a really strong moist anomaly. So this is pretty interesting. And I also want to highlight the region where we calculated the buoyancy. So that was between 850 to 600 hectopascals. And we can see here that the moisture anomalies don't really change that much, and it's not really capturing all of the effects well that is happening in the entire column.
Is that what you're referring to as the LFT?
The what?
600 to 750 is a lower. You had LFT in some of your earlier missions.
Oh, yeah, it's the LFT. Yeah, that's the LFT. Yeah. Mm-hmm. Okay, so next I'll be showing the temperature and omega cross sections. So same thing here. Let's focus first on the prior days before the heat wave. So here we'll notice that there is a slight negative temperature anomalies near the surface, also where we find that region of upward motion. However, at the onset of the heat wave, where we had the downward motion, we do see some warm anomalies. But this is not just happening near the surface. This warming is occurring in the entire column. So this is interesting. So the moisture and the temperature anomalies change throughout the entire column, and we see that there's some upward and downward motion associated with this. So what we're going to do next is not just look at moisture or temperature separately, but we're going to be looking at the moistatic energy. Specifically, we're going to be looking at the column integrated moistatic energy deficit. So here is the column MSE and minus the saturated column MSE. What we want to do first, though, is see if there's any relationship between the subsaturation and the column MSE deficit. So the way we do this is we're going to be making a scatter plot of the lags from day -7 to +7. And we want to see if there's any relationship between the subsaturation and column MSE deficit. So here are the scatter plots for all of the regions over India, East Asia, Australia, and the Yucatan Peninsula. On the x-axis, we have the subsaturation, and on the y-axis is the column MSE deficit. And we can see right away that in each of the regions, there's a very strong linear relationship between these two variables, as noted by the R values being greater than like 0.96 from all of the regions.
So sorry, the subsaturation is just at a couple levels, and the CMSE is at all levels. Is that right?
Yeah.
Okay.
It's the whole column for the CMSE.
So you're saying that those couple levels are representative of what's going on in the whole column?
Right.
Okay.
Yeah, so there is a linear relationship between these two variables. So changes in the entire column MSE deficit may be useful to explain heat waves. So the way we do this is we're going to define the column saturation deficit budget. So this is our column MSE deficit. What we do first is take the time tendency of this, and after a few steps, we get the following expression. So this first term on the left is the horizontal advection of MSE. This next term is the column process, which just has contributions from the vertical advection of MSE, radiative heating, and sensible and latent heat fluxes. And this last term here is what we'll call the non-WTG warming term, and this arises from deviations from WTG. These first two terms, the horizontal advection of MSE and the column process, are usually what make up the column integrated moist static energy budget. However, this last term does not. So what is that term, right? So in order to understand this term, we have to remember that in the tropics, there is a weak temperature gradient, a weak horizontal temperature gradient. This implies that there's also a weak pressure gradient. In the tropics, you can also assume that pressure surfaces are proportional to isentropic surfaces. And let's just say that on the XZ plane in the tropics, those lines are lines of constant entropy. Let's assume that there is some diabatic heating source, such as a cloud or convection. Diabatic heating can cross the isentropes, but it cannot move them in the tropics under WTG. So under WTG balance, diabatic heating doesn't move isentropes. However, if you consider any deviations from WTG balance, such as horizontal temperature advection or adiabatic lifting, if we look at the same XZ plane with the isentropes, if you have deviations from WTG balance, you'll find that the isentropes start to compress, so it warms up the column. So if we go back to our column saturation deficit budget and just focus on this last term here, and note that the column MSE is a saturated column MSE is a function of temperature and saturated specific humidity. And after a few steps, you get the following expression, where the non-WTG warming term is equal to the horizontal advection of saturated MSE minus the vertical advection of dry static energy by deviations of WTG. So deviations from WTG are what can cause advection of these heat to contribute to any column temperature changes in the tropics. So now let's try to plot all of those components of the column saturation deficit budget. And I'm just going to reintroduce what those terms were in word form because it's easier. So the column saturation deficit tendency would just tell us if the column will either moisten or dry. The horizontal advection of MSE will tell us if the moist static energy is being transported into or out of the region or out of the column. And the column process tells us if any changes in the moist static energy, vertical advection, radiative heating, or surface sensible and latent heat fluxes will contribute to the tendency. And the last term, the non-WTG warming term, will tell us if any deviations from WTG kind of result in this isentropic compression. So now we can take a look at the column saturation deficit budget terms one by one. So here, the black line would be the column saturation deficit tendency. I'm just going to refer to this as the tendency because it's a mouthful to say. And the green line is the horizontal advection of MSE. The gray line is the column process. And the orange line will be the deviations from WTG. So this is the lag composites over India. The x-axis, the days. The y-axis is the anomalies. So one by one, we'll go through these terms. So the tendency, the black line, prior to the onset of the heat wave, is slightly positive. However, it does become negative at the onset and then becomes positive again. And in this region, the horizontal advection of MSE doesn't change as much. It's slightly positive and slightly negative at the onset, and then it kind of goes to zero. And the column process here doesn't really contribute as much as well. It's very slightly positive prior to the onset of the heat wave. The orange line, the deviations from WTG, are really what's explaining the evolution of the tendency term here. So as you can see, the orange line is very closely following to the black line throughout the entire range of days. So prior to the onset, there is some drying tendency. Similarly, over East Asia, the black line, it kind of is negative prior to the heat wave, so there is a drying tendency, and it becomes positive a little bit after. Here, the horizontal advection of MSE and the column process don't really change at all throughout the entire range of days. And it's that orange line, the deviations from WTG, that are really closely following how the tendency evolves. Over the Yucatan Peninsula, there's also some tendency of drying prior to the onset of the heat wave, and then becomes positive a little bit after. The blue line here has more contributions in this region than the other two. So it is positive prior to day 0 and becomes negative a little bit afterwards. And the column process doesn't change at all. And the deviations from WTG, though, are really what's following closely the evolution of the tendency term, right? They're both negative at the onset of the heat wave and positive afterwards. Over Australia is very similar. There is a tendency of the column to be drying prior to the heat wave. Here, the horizontal advection of MSE is slightly positive throughout a wider range of days, a little bit prior and a little bit after the onset of the heat wave. Here, the column process does not change at all as well. But what's really driving that tendency to be changing is the deviations from WTG, as you can see with the orange line. It's following very closely to the evolution of the tendency. So the non-WTG warming term largely aligns with how the column saturation deficit tendency is evolving in all of the regions, regardless of how the hemostatic energy is evolving. So this means that there probably exists a deviation from WTG that can cause the isotopes to be squished or squeezed, and this results in a warming column and therefore a heat wave. So in summary, this might imply that the processes that lead to the moist tropical heat waves might not be in WTG balance. So in summary, yay, it's almost done. I want to summarize the key points, and I'm going to do it in a kind of a picture format because it's easier for me. So here on the x-axis is the same range of lags, -7 to +7, and on the y-axis would be like pressure levels. And we're just going to draw some isotopes here, some dry static energy lines. So prior to day 0, we saw that the buoyancy was positive, and we also saw from the cross-sections that there was a moist column and some upward motion, probably indicative of some precipitation occurring. However, we also noted that there might be a deviation from WTG occurring just a little bit before the heat wave, which leads to some downward motion, leading to the isotopes to be compressed. And then the column will warm. And as the column warms, this means that the saturated column MSE or the saturated specific humidity is going to go up. The subsaturation will be stronger, and this will cause the buoyancy to be decreasing. At the same time, this is all contributing to changes near the surface that are, like moisture near the surface is increasing, so the wet bulb temperature is increasing as well. And finally, at the end, the isotopes do start to go back to their normal state, and the buoyancy kind of goes to approaches 0. Okay, so before I end, I just want to give some ideas for where this project could be directed afterwards. So one of the questions that you may ask is what causes the deviations from WTG? So, and also what causes it to end. Something else that could be explored would be comparing different characteristics of the heat waves. So their duration, the intensity, or the frequency of the heat waves, and if they all exhibit this kind of deviation from WTG that we saw in the composites. Another direction for this could also be to look at any synoptic or large-scale systems that could be associated with these heat waves, such as like tropical depression type waves or some extratropical influence as well. Another direction where this could go is to try to look at the heat waves if there's any connection with some climate modes, such as the Madden-Julian oscillation or ENSO. Okay, that's it. First, I want to give some acknowledgements. So, of course, my advisor, Angel, I forgot where he's sitting. Oh, he's right there. Of course, thank you for accepting me into this group. I've been having like a really fun time here, even though sometimes I have like a poker face and you can't tell. But I've been having such a fun time here, and I love doing research. And I want to keep going, and I want to keep learning about the tropics because it's so interesting to me. I also want to thank my committee, Larissa and Ankur, who I think is watching online, and also my lab group, the Large Scale Tropical Dynamics group. A huge shout out to Victor, the research scientist in our group. He somehow has all the data in the world in his laptop, so I can just ask him for something and he has it. So he's been really helpful. And he also gives great advice, great insights, not just scientific, but also personal. And he helped with the calculation of the budget that we saw here. I also want to thank all the professors here and the staff. Everyone's so welcoming here, and I also want to thank my friends, Ali, Idamis, and Shane, who are sitting in a row here. They're right there too. I would not have survived the first year here without you guys. Like, it was so hard. Like, I was like, I don't know how to do these derivations. Like, please, Ali, help me. Like, and just like emotional support and going to Indy for waffles, it's been a good time. I also want to thank my friends back home, my family back home. So yeah, and if you're wondering, that's a picture of when I went to see the eclipse. You can't see it though, because I took it on an iPhone, but you can kind of see it right there, and you can see that the ring of the sun. Yeah. So I'll be happy to take questions or suggestions or anything.
All right, so I can get up. So starting off with students, do any students have any questions for Sofia?
Please.
Move your back there.
Hey Sofia, super interesting talk. Might be a naive question, but I'm wondering how these different regions topography could be playing a role into some of your results. Do you have any insight whether topographical features would cause any changes in your lag and differences within the regions, or could be something else?
Yeah, that's a good question. I hadn't thought of like the topography that much before, but it could very be influence how different they are in the regions. So like over India, there's probably like the mountains are kind of stopping like how the moisture is evolving as well. But yeah, I haven't really looked at it at the geography that much as well. So
To add a little bit to that, we did see north versus south hemisphere difference, but we didn't show it because that's a topic for another day.
Yeah, there is some difference between those hemispheres, but geography, I didn't really take note of that.
Is there a climatological difference in terms of frequency of these heat waves based on the 4 regions you decided on? Is there trying to link that to larger patterns, and so MJO, is there anything there, or is that yet to be explored?
Yeah, they do have like a seasonal variation. So can I show like extra plots? Like, I don't know how to show it without showing like too many extra plots, you know? Because I don't want to go through everything. I think I have it next though. I do have it, okay.
Question plans.
Yeah.
So we did count like how frequent the heat waves are occurring like for each month. So they do have like some seasonal variation. So over India, you see that it's a little bit prior to monsoon season. And in Australia, it's right at its peak of its summer, or like it's Northern Australia monsoon season. So there are like different things that could be explored there. Yeah.
Maybe just to follow up on that, why does the Yucatan have a peak in June? It seems almost erroneous compared to, it's like a bimodality. Have you thought about that?
No, not really. I haven't thought about it. But it could be an error in my calculation, how I'm counting them. Yeah, or it could be something very interesting that I should look at, but no, I don't know.
I don't think it's an error. I think that there's actually something going on, like that there's two ways that you could get them there, but we haven't examined one. So.
That's true. That's true. Good point.
Quinn, and then we move on to like general questions from everybody.
A really interesting talk. I guess I was interested in, these are relatively long heat waves, 5, 10 days. So I guess I'm surprised that there would be such a long-term deviation from the temperature gradient. Apparently, I guess I was interested in if you had any thoughts about, or if there have been any looking into where these long-term deviations from the temperature gradient would be coming from, and how they're staying stable.
Yeah, I don't know where these deviations are coming from. It could be like a really strong wave, maybe, that's very different from like any other type of waves. I don't know. And there could also be like, I think we were talking about this earlier, like some influence from like a more planetary scale, like maybe some signature from ENSO or something like that, that could be causing these long-term trends.
Yeah, I have a couple of ideas of what's going on. One that actually shows up in one of the locations clearly is that there's a clear extratropical wave train coming in, so that, extratropical rocky waves, they're not in WTG, they can come in, cause a lot of subsidence in the region, so they're kind of just washing the essence. So it can come from mid-latitude dynamics. There's a couple of cases that do seem to be more tropical in origin, we're not sure. My basic, hypothesis that I kind of threw at Sofia is that WTG, if the scale of the motion is larger than the deformation radius, then WTG doesn't apply to it, so that we can potentially see motions that are fairly large scale for tropical motions that could be driving these heat waves. So, and then one of the composites that, again, like a stuff that we don't have time to show, but you do see these very large ridges that seem to be forming in the region. Why do we only get the heat waves locally with such large scale patterns? Like, it's a good question, right? But it does seem there are potential mechanisms. But if you're surprised about being on WTG, we're surprised too. We're kind of expecting something different, to be honest. So questions from the audience? I think Matt.
Well, you answered a lot of what I was kind of speculating about. I've never thought about tropical heat waves before, so this is interesting. My impression is you have kind of a 1-2 punch to achieve it, sort of convergence, unsave a lot of moisture down from the rain, and that lingers due to the second part, which is subsidence. And that's what I was getting at in my mind is what can organize the subsidence? And you're suggesting maybe traveling waves from mid-latitudes can penetrate maybe easterly waves. I'm pretty naive about this topic. My question is there a sequence in situ regionally that could cause that 5-day transformation, or do you need something to propagate in to make that happen? I don't know.
Yeah, I don't know. Just based off the composites, I would say you need like some sort of larger scale forcing to make this happen. And that's just based off the composites. I think if we want to go in a little bit deeper, we would have to try to differentiate those composites, or like make some sort of cluster analysis to see if there's any more clear regional contributions to the heat waves. But yeah.
To add a little chip into this, like in the Australia case, it's very clear that it's a mid-latitude train. Like you can see it in the 500 hectopascal potential ice just coming in from the Southern Ocean. The other cases, it's not clear at all, and we don't really know what triggers them. Like it could be some local upscale feedback that
Plus,
triggers.
the regions are so different. They
Right.
just have different.
Yeah.
things happen.
Yeah.
And some of them do look surprising, like the Northern Hemisphere ones, some of them look surprisingly similar, even though they're very different. But the Southern Hemisphere ones are like very completely different from the Northern Hemisphere ones. That's the one, that one that we can tell. John and then Larissa?
Yeah, fabulously interesting, Sophia, and very well presented. This is a great presentation.
Thank you.
I'm wondering if the subtropical jet is a factor here. Waves that might develop along it. The only thing that makes me pull back a little bit on that suggestion is that it's in the heart of the warm season in the northern hemisphere. The subtropical jet's displaced far to the north. It's not near 20 degrees north. And so, but it would be a really good candidate for looking for, imposed subsidence on a region. But maybe it doesn't quite work from that other perspective. So anyway, I guess I would just say, in addition to the extratropical wave trains, which might have a role to play apparently in the southern hemisphere, maybe not going too deep into the extratropics and thinking just about the boundary between them and the dynamics that go on at the tropopause of that boundary might have something to do with it. But it's fabulously interesting, just great,
Yeah.
really interesting.
Thank you.
Yeah, I mean, I would tend to agree that there might be worth looking at subtropical.
And it strikes me too that the whole notion of waves on the subtropical jet is understudied in terms of waves everywhere else. Waves on the polar jet are well studied, waves in the boundary layer are middle, lower troposphere are well studied, but that particular spot is one that it's really hard to find a rich literature on that. And maybe it's worth investigating. So,
Yeah.
for what it's worth.
Yeah, and I think we can chat offline about this, but like the north versus south hemisphere difference kind of suggests to me that there is something important about this subtropic and mid-latitude interface, because the southern hemisphere storm track is year-round, right? So you can see extratropical motions maybe coming in even during the summer, offshore summer. The northern hemisphere one is the one that you can shoot a lot of possibilities there.
Right, yeah.
That could potentially answer the question. Larissa?
Yeah, I'm just wondering, it seemed like there was a different lag relationship in different places between the heat waves and the buoyancy. So were you kind of thinking that the buoyancy is ending heat waves that were different lengths, or kind of how were you thinking about that relationship, or do you have thoughts, I guess?
The buoyancy evolution?
Yeah, the buoyancy revolution relative to the heat waves, yeah.
I didn't think much about how the heat waves were ending. I did know though, as you approach the last day, the lag day 0, the buoyancy did kind of approach 0. Yeah, I haven't really thought much about what could be causing it to end. Maybe it's just the end of a wave train or the end of the wave, but yeah.
It just seemed like the heat wave didn't line up with the buoyancy maximum, right? So you were kind of trying to reason about the heat waves using the buoyancy. Does my question make sense, or?
Yeah, I think it comes down to the nuances of the buoyancy calculation. My hypothesis on the matter is that the buoyancy, we're using a buoyancy metric based on previous work. My suspicion is that it underestimates the contribution of the free troposphere even by including even the framework that we're using. So when you look at the subsaturation, I think that aligns better with the heat wave than the buoyancy itself. So and this is what we were talking, we could try, before writing up the completing the manuscript, we could try modifying the definition of the buoyancy a little more to see if weight the free troposphere higher, to see if we can get a better alignment. But I feel moderately confident that part of the issue is that we're still underestimating how important the free troposphere is to the total buoyancy. Yeah.
The connection between the buoyancy and the column wave static energy deficit that you made was really nice, and I like that idea of using the column wave static energy deficit.
Thank
and you presented that really well.
Thank you.
It was a really nice talk overall.
Thank
Should
you.
led with that.
The buoyancy stuff with the lagging is also an issue that Victor and I have found with rainfall too, that we can't
Oh, really?
totally align it. And again, Victor has found that it aligns a lot better if you weigh the free troposphere a lot more heavily. So again, but we haven't found like a definition of the buoyancy that works perfectly. Yeah. Brad, and I think that'll, unless there's one more question.
I like how, I mean, at the beginning you were talking about the key, you have this rapid convection that equilibrates everything, and you gotta shut that down. And it was really nice showing that departure from the mean temperature gradient is what compresses the isotopes, makes it stable, and so there's some kind of capping, something, right? But then you're talking about some large-scale substances. Why does the frequency of these, the spatial distribution of the frequency of these heat waves, it's still very kind of local? Where does like sea surface temperature, anything like that come into play? Why would you get these local regions that you've chosen, but it's probably being driven by this larger scale substance? Like it's not suppressing convection everywhere.
I don't know like why the such a large scale would only be influencing like a local process. It could be related to maybe the sea surface temperatures. Like a lot of these regions were around the coast, so there could be like some influence from there too. Like a higher sea surface temperature would help kind of destabilize the surface. Yeah. So, but other than that, I'm not sure.
So here's a hot take. I think the SST influence comes from like the areas of high SST are the areas that are also really humid, have a lot of convection. So my thought that I've had is that these shifts in these regions of high moisture and convection can develop large-scale waves. And then the reason why you get a heat wave in these regions are that these regions have land atmosphere or like surface boundary layer processes that they're already like hot and humid in the first place. So all you need is to kind of like bring in something like substance that kind of just takes it over the edge. So I think you can have locally, you know, the head of the Bay of Bengal, yeah, that's really warm in there, so that can lead to the heat waves. But like under WTG, you know, large scale adjustments that happen in the tropics, you can actually have that occur remotely. So it could be somewhere else that actually is driving the large scale waves that are triggering the heat waves in this region. And this region just happens to be at the cusp, just because it's hot and humid there to begin with. Angela, and then we wrap it up.
I want to build off that, which goes back to Rudra's comment. Can you go back to your first map that shows where this, like, is it on the lee side of terrain?
Oh, the very first map?
Yeah.
Oh, God.
Or, like, where is it related to terrain? It just kind of
Here,
depends
let
back
me
to
just-
what you were just talking about. Like, the very first map, yeah. Where are these hotspots relative to the topography or the coastlines? So they are maximized near the coast.
Yeah.
Huh. It wasn't so much as a question as I wanted to have this in my brain with those questions. So I think there's really something to that coastal and particularly some of the topographic regions that are in that area.
Yeah.
Yeah. Really cool.
Yeah, I do think that there's
Yeah.
like a local land atmosphere.
Yeah.
All right, so that's a wrap. Thank you all for coming. Thanks, Sofia, once again for your presentation.
Thank you.